The following is known as the haloform reaction. It's another fairly special case reaction, but it allows us to convert a methyl ketone into a carboxylic acid. Now, in terms of history, or at least reactions that we know who originally discovered, this is one of the oldest organic reactions out there. In fact, the first known example of this reaction dates to 1822. A few years later, 1832, a more famous chemist, Liebig, also found an example of this reaction. Not much really was done with it at that point, and then really see the use of this reaction start with Adolf Liebig in 1870. But again, this is a reaction that will allow us to take a methyl ketone specifically. If your ketone's more complicated than a methyl ketone, this reaction doesn't work. But if you take some sort of methyl ketone and you typically use hydroxide, and it has to be hydroxide as the base here for reasons that we'll see later in the reaction. But you do that in the presence of bromine. And as a result, we get a carboxylic acid as the product. So the first part of the mechanism is pretty straightforward. We have a base here, and base will remove the alpha hydrogen to form an enolate. And just for space, I'm going to abbreviate the aromatic ring with pH. So we've got our enolate. The enolate can add into a nucleophile or an electrophile. And as you've probably previously seen with halogenation of alkenes, we know that something like Br2 can be an electrophile. And so we've done, at this point, an alpha bromination. But the thing is, and this isn't always the case with these reactions, we've added an electron withdrawing group to the alpha hydrogen, or the alpha carbon. And so these hydrogens on this alpha carbon are now more acidic than they were in the starting material. Well, since there's two more hydrogens on here, what happens? The exact same thing. We can form an enolate, and then the enolate attacks another molecule of bromine, and we get a second bromination. That one remaining hydrogen, though, even more acidic now. So the reaction happens a third time. And so as a result, we now replace all three of those hydrogens on that alpha carbon with bromines. But the reaction's not done here. And the reason the reaction isn't done is because of those three bromines. Now, we know if we have a ketone and we've got hydroxide present, hydroxide can function as a nucleophile, and this moves towards forming the hydrate. A reaction we usually don't worry about too much because the hydrates are not very stable and they revert back to the starting material. But what if instead our ketone had a leaving group on it? And we might not think of CBr3 as a leaving group, but it turns out that CBr3 minus is the conjugate base of bromoform, CHBr3. Bromoform has a pKa of around 22. And so is CBr3 minus a good leaving group? Probably wouldn't classify it as a good leaving group, but it's good enough. And if we have something to help drive the equilibrium forward, it's more than sufficient as a leaving group. So if this O minus adds its electrons back in, we kick out CBr3. As a result, we form a carboxylic acid, plus the bromoform anion. And then between that new anion that's formed, plus the hydroxide that's in solution, those are going to easily deprotonate the carboxylic acid we just made. And so while this step might not have the best equilibrium, this step here of deprotonation to form the carboxylate salt is going to go only in one direction. And then upon quenching with acid, we form our carboxylic acid.